Okay, guys. So yeah, thank you very much for joining.
Shamidu, better if you could introduce yourself for a short introduction.
Yeah. So a very short introduction. My name is Shamidu Monasinghe, and I'm a general class license ham operator. My call sign is for Sierra 6 Charlie Mike uniform or for a 6 EMU. By profession, I'm a software architect with around 22 years of industry experience. I have been working with various technology stacks on IT, but as a hobby, one of my hobbies is a bit of electronics and embedded development. And I also done a bit of a commercial IoT type of work. Yeah, and then I recently became a ham operator, and then my other hobbies, I'm into wildlife photography and I play a bit of music. So yeah, so you can reach me. I think I'm on the RSSL group, and you can reach me anytime. Like with regards to inquiries about this content or anything related to ham radio. Yeah. So today we are going to discuss a bit about radio theory and communication techniques. So this might overlap with what you have discussed so far. So I have not joined the other session, but this is with regards to an introduction to radio theory. So basically, I think today we'll cover a bit, and then maybe in a later session we'll continue. Like if you talk about this radio theory, there's a bit of like hairy mathematics involved. So we are not going to go there. I'm no maths expert, let me give a disclaimer, but we'll talk a bit my idea here is to give you an intuition, a visual intuition about these things, we are good. There's a lot of maths involved, like Fourier transforms and different transforms, digital signal processing, and all that in this modern radio equipment. But what we are going to get is intuition of how it works, and also give you guys a head start if you want to go into this deep stuff, to give you guys a head start to doing that. So that's my goal, right? So with that goal set in place, let's continue. By the way, which language should I use? Should I focus more on Sinhala or English, or are there like Tamil speakers here who doesn't understand Sinhala, or can I mix and match? How does it work, Aruna?
You can use mixed language, Chamidu. Mostly it's better to conduct in English, but there's no restriction. You can use.
Okay, so yeah, so I'll primarily use English as my language, and then by the way, if you guys don't understand, or like if you feel that in Sinhala might be a better, I can just feel free to raise your hand and jump in anytime with questions. So I'll try to address it. Sometimes it's sometimes it's difficult in Sinhala because I also don't know these terms in Sinhala for some of these technical words. But yeah, we can go ahead and let's get started.
But they can ask questions in Sinhala. It's okay.
Of course, yes. Yeah,
I think Tamil, of course.
Yes. I don't understand. I'm sorry.
Neither of us understand. But other language, English or Sinhala, both you can use it for Q&As.
Cool.
Okay.
Okay, then let's dive in. Okay, so now this is a very high-level agenda. So basically today what we are going to focus on is first, radio communication involves radio waves. So we'll get an introduction to what is a wave and their properties, like what do we need to be aware of, when we basically, I think this is very important, when we decide antennas, when we design antennas, and, basically when we lay transmission lines, we need to be aware of these certain properties of RF waves, and also properties of any wave in general. That is part of being a ham operator, is that we do our own DIY stuff. Even though there are commercial antennas available, a lot of us, we design our own antennas, and like we lay our own transmission lines and things like that. So, and then basically we'll discuss a bit about how these waveforms can be represented in different domains on what we call this frequency domain or spectrum analysis. And then we'll talk a bit about communication systems and how about a bit about modulation and a bit about AM and FM and single sideband. So basically, depending on what time permits, we'll see. And also, I'd like to do a couple of simple demonstrations as well. So let's dive. So what is a waveform, right? So essentially, a waveform is a disturbance that transfers energy through a medium or vacuum space, right? So for example, like when you go to the ocean, you see waves, right? So, and if you drop a pebble into a pond, you will see a wave that travels and that transfers energy. So basically, in a waveform, the physical medium doesn't move, it oscillates, but the energy gets transferred. And in the case of electromagnetic waves, you don't need a medium, it travels through space, right? So even light is an electromagnetic wave with very high frequency, right? What are different types of waves? There are mechanical waves, like sound and water waves. And then if you take mechanical waves, there are two types of waves. I forget the English term, but what you call this theoretic taranga and anvayama taranga. So basically, how the particles in the medium move towards with relative to the direction of the wave propagation. I think we all learned about this during our O-level science classes, if I'm not mistaken. And then we have electromagnetic waves, which propagate by using an alternating electric and a magnetic field. So these waves don't need a medium, right? And there are different type of EM waves, like radio waves, what we use for radio communication, and then light waves, and also X-ray. Those are electromagnetic waves, which has an electric field and a magnetic field. So basically, like electric field and a magnetic field, they are perpendicular to each other, and the wave propagates perpendicular to that. So what is the simplest type of waveform that you can have? Here I did a bit of an animation using Manim animation library. So basically, to demonstrate what a sine wave is. So basically, let's take a rotating vector and plot the projection on the y-axis, right? So this shape is a sinusoidal. So if you did a bit of trigonometry, you will know that what a sine wave is, right? So now a projection of a rotating vector on the axis is a sine wave. So at any given point, you can see that amplitude here. So this is a sinusoidal waveform. So we can present the y-axis as a trigonometric function, a sine function of the x value. Typically in waveforms like radio waves and electrical waves, this y-axis we represent by time, right? So yeah, any questions so far? Do you guys? I hope like you guys have some sort of an idea about this about trigonometry and what a sine wave what the sine function is. If there's any sort of clarification that is needed, please raise your hand. I will also share this slide deck after this is done, and also I can share the code for this animation as well if you guys want it. Yeah. So moving on, right? What are some properties of a waveform? Right? There are certain properties that we are interested in when we describe a wave. To fully describe the waveform, we need this a couple of these parameters. For example, the amplitude of a waveform is basically the maximum displacement. Now, if you guys have studied a bit about simple harmonic motion, or what you call this saralanuvarti chalita, like of a small angular motion of a pendulum, or a small oscillation of a spring that is hung by a spring. Basically, all of these motions are like simple harmonic motions, and that generates a sine wave. Amplitude is the maximum displacement of that harmonic motion. Right? So I have, like, you can see from the equilibrium or the 0 point to the maximum displacement, we measure the amplitude. Right? So it's not the peak to peak. So for example, now we call these high points crests and these points troughs, right? So amplitude is either this value or the negative of this value. So that's amplitude. And the wavelength, the length of a waveform, like if you can see this waveform repeat, so we call this a periodic signal, right? Whereas, there some signals can be a periodic where you don't have a repeating period. But in RF and communication, we mostly our carrier frequencies are always periodic signals, so we don't worry about aperiodic signals. But now in a periodic signal, the wavelength is the distance between a crest or the distance between trough is a wavelength, right? So basically, any similar point in the waveform we can take. Although we say crest to crest or trough to trough, but any similar point, 2 points, if we can measure the distance, that is the wavelength, right? And the frequency is cycles per second, right? So how many complete cycles, right? So this is a cycle, right? Starting point and to come back to the same point. So from here to here, this is a cycle, right? So how many cycles do we complete per second? That is measured in hertz, right? So if you take the time period for a cycle and get the reciprocal of that, 1/t is the frequency. So I think the next slide, we are going to discuss a bit about that. Okay, so here we are discussing about wavelength. So distance between two consecutive points in phase on a wave, such as a crest to crest or trough to trough, measured in units of length, right? So basically, wavelength is measured in typically meters. When you are doing calculation with SI units, we use meters, but we can use nanometers or micrometers as well. So what is amplitude? There's a bit of a lengthy description here. Midline to crest, the displacement. So basically, for mechanical waves, we can measure this using, again, meters. Like, let's say, for example, if you are measuring ocean wave, Typically, amplitude can be measured in meter. So now, in a electromagnetic wave, it is measured in volts per meter. So that's like the electric field strength, or Tesla's for the magnetic field. So I think we are not going to talk very deep into this. And in the case of an electrical signal, we can use basically volts. Right? So in RF, we measure it in volts per meter. So that's like the electrical field strength. So this slide gives you a bit about the frequency. The period is the time required for one complete cycle, right? So frequency is a number of complete cycles per second measured in hertz. So basically, frequency and period are inversely related. So basically, frequency is 1 over t and t is 1 over f. I think this is like pretty straightforward. I don't think we need to dwell a lot on this. And higher frequencies mean shorter period, right? So basically, as the frequency goes high, the period decreases. So now let's take a look at this. I also I mentioned earlier as well, like we are more interested in getting a visual kind of like intuition for this, right? So a sine wave can be represented by this expression or formula. So a times sine 2 phi ft plus phi. So basically, don't worry too much about it. If you don't understand this at a glance, don't worry too much about it, right? So what this means is a sine, any waveform, we can describe in terms of frequency and time, and also amplitude. A is amplitude, right? And this phi is the phase angle. So don't worry too much about this expression, but let's do a visual demonstration for this. For that, I'm going to use this tool called Desmos. It's a web application. It's basically a graphing calculator. Let me just open this link and show you. Okay. So here, let me give you a bit of an introduction to Desmos here as well. Basically, it is a graphing calculator. On the left side, you have this pane where you can enter different expressions, which will be graphed here, right? So basically, now here I have two expressions, y equals a sine 2 phi fx, right? So here, this is my x-axis and this is my y-axis. I assume that everybody here has a bit of an understanding of Cartesian geometry. What a graph is. If there's anybody who needs some clarification, I know, like, don't be ashamed or anything like that. Even, for me also, like, it's been a long time since I studied this, right? So if there are any clarifications that is going to help you, please raise your hand, or even you don't need to even raise your hand, just ask the question. I'll explain. And there's a couple of experts here as well. If I'm not mistaken, Tarang is here. He's an electronics engineer, so he knows a lot about these things than me, and Arun also. If there are any questions, guys, please feel free to raise your hand and ask, right? Okay. If there are no questions, let's continue. So this is, now I'm graphing these two things. Now, right now, phi is 0. So that's why you just see one wave. And then amplitude, this is amplitude, right? So basically, let me just modify the amplitude, right? So when you increase the amplitude, so you can see basically the displacement. If you take the amplitude to 0, you don't see the wave, it's a straight line. Now, as you increase the amplitude, you see the waveform getting bigger. So this is amplitude, right? So right now, my frequency f is 1. So it takes 1 unit to complete a full cycle, right? So assuming that this is axis is time, and assume that this is in seconds. Now this waveform is a 1 Hertz waveform. Yeah. And then let me try to increase this to 2. Yeah. Okay. So basically now you see within 1 unit of time here, 1 second, we have 2 cycles of the wave, right? So now this is a 2 Hertz wave, right? Okay, so let's me just set this amplitude to 1. And let's talk a bit about this phase angle phi. Now this phase angle always comes usually like when we talk about 2 or more signals, right? So now we have a first signal that is 2 phi fx. So a sine 2 phi fx, this signal, and then the second signal is 2 phi fx plus phi, and right now phi is 0. And let's try to increase this, right? So the blue signal is the second one, right? Now when you increase this, what happens is that the signals go out of phase, right? So basically now this is in radians. So this phi is in radians. Now, so you see that this blue signal leads the red signal by this certain angle. Right now, I mean, if you are familiar with phasor diagrams, you can you remember that, you know, like you can show this as the angle between the two phasors on the phasor diagram, but don't worry about all those things, right? This is just to give you an intuition about this, right? So I don't have it here going negative. So basically, if it is going negative, you see the second signal will be lagging. So that is what you call the phase angle. It's the same waveform, same frequency, but the first waveform starts earlier than the second waveform. So that's what essentially a phase difference means, right? So I assume everything is clear. Yeah. Any questions? No. So I don't know. Is it always like this? No feedback from the audience? Okay, fine. I mean, as long as you guys understand, that's fine.
Please ask questions.
Yeah. Okay. So please feel go around and play with Desmos. It helps you to understand a lot about. I mean, getting a visual intuition is the most important thing as a ham operator, right? So yeah. Now let me go back to the slideshow and continue. Right. So this is okay. So this is the general formula, the time domain formula for a sine wave. So at any given time, the value of the sine wave, the y coordinate, can be expressed as amplitude times sine 2 phi ft. F is a frequency, right? So this 2 phi f is again like sometimes referred to as omega, or the angular velocity of that rotating vector. Sometimes if you've done electrical engineering, you have probably come across this, right? This 2 phi f. In our case, using 2 phi f is better because we deal with frequencies. And then 2 phi time plus phi. So the Desmos demonstration was about that, what is actually a sine wave. Okay. So right. So now this is a very important formula, right? What is the speed of a wave, right? So speed of a wave depends on the medium, right? So now, for example, the speed of sound is somewhere around 300 something meters per second, if I'm not mistaken, in air, right? And if you take a solid medium, sound travels faster. So it's the velocity depends on the medium, right? But in our case, the speed of electromagnetic waves in vacuum is 300 to the power by 10 to the power 8 meters per second. So yeah, there it's very fast. That is the speed of light, right? So basically, electromagnetic waves travel in vacuum at the speed of light. But just keep in mind that in solid conductors, the speed is different depending on the type of wire. So sometimes when I don't know whether you have learned about this, when you design antennas and things like that, there's this, it's slightly slower than the speed of in the vacuum. And then it is called velocity factor. So we have to factor that in as well when we calculate. But when we calculate the wavelength of a RF signal or radio frequency signal in vacuum or in open air, we can take it as 300 to the power 300 to 10 to the power 8 meters per second. Yeah. So how the frequency and velocity and wavelength relate is the velocity equals frequency times the lambda or the wavelength, right? So if you take lambda in meters and hertz in hertz is the inverse of period from last couple of slides. It is the units are seconds minus 1, like so 1 over seconds, and then multiplication of that gives you meters per second. So meters over seconds, right? So the units match, and from this formula we can derive a couple of stuff. So sometimes we need to, usually we don't calculate velocity, right? So we know with RF radio waves, it's always, we take it as 300 10 to the power 8. But now we typically need to calculate the frequency given a wavelength or wavelength given frequency, right? Sometimes in amateur radio, we typically use wavelength to refer to bands. Like, I think, I'm sure if you heard our nets, or, if we listen to our ham radio operators talk, like we talk about this 10 meter band, 14 meter band, and then so 7, like 10 meter band, the 40 meter band, which is like in the 7 megahertz range, and 20 meter band, which is 14 megahertz, like that. So we frequently refer to these frequency bands in terms of their wavelength. So it's a range of wavelengths, right? It's not just one figure, but we say, like let's say, for example, if our 40 meter band is in Sri Lanka, in this region, it's 7 megahertz, 7.2 decimal megahertz, right? So the wavelength changed slightly, but we call it the 40 meter band, like that. So as the frequency increases, the wavelength decreases, as we discussed earlier, right? So let's maybe do a simple example, right? Let's take one problem, and let's find the wavelength of a 10 megahertz RF signal, right? So here I have given the velocity. It's fixed, right? So in vacuum, the velocity of RF radio wave is fixed, with regardless of its wavelength or frequency, the velocity is fixed. Hence, we can calculate the other two, right? So let's go step by step, right? So step 1 is known if F is 10 megahertz. It's 10 times megahertz is 10 to the power 6, right? So velocity is given. So we can apply the formula. We can rearrange lambda is V divided by F, right? So 3 times 10 to the 8 divided by 10 times 10 to the 6. So that is here this is 10 to 7 and this is 10 to 8, and I think it's 10 to the power 1. 3 times 10 to the power 1 is 30 meters, right? So the wavelength of a 10 megahertz signal is 10 meters, right? So in a conductor, this will slightly differ. So when we are doing antenna calculations, this is slightly differ, but in air, it's 30 meters. Is this calculation clear to everybody? I don't know whether you guys covered this in a previous session. I'm not aware, but this is typically you get a couple of questions from this in the exam, right? Okay. I think it's cool. Let's move. Right? Okay, so for 100 megahertz, it's 3. So you can see, like, so as the frequency increases, the wavelength kind of like shortens. So this is an important property. That's why, that's one of the reasons that we use RF in communication. We'll come to that. Okay, so far we've talked about sinusoidal waves. You know, whether it's a sine wave or a cosine wave, the shape is the same, right? They are just 90 degrees apart, if you remember your trigonometry. But now in our real world, we don't just deal with sine waves only, right? So we have to deal with square waves, triangle waves, and sawtooth waveforms and arbitrary waveforms. So these things are like this. Things like square waves, triangle waves, and sawtooth waves are very commonly used, you know, in communication as well as different stuff. Like even in like digital music synthesis, we use like triangles and sawtooths. I mean, if you are into this, you'll see. So these things are like, we have specific names for these because we use them frequently. And then there are arbitrary waves as well. You know, like if you take speech, when I speak, the shape of the wave that is emitted from my vocal cords is arbitrary, right? So the amplitude and time varies arbitrary, and this is not actually a periodic signal as well. So it's a periodic, so it changes, you know, with what I speak, right? Okay. So I think we have a rough idea about, kind of a high level idea about different type of waveforms. And okay, so this is a very important slide, right? Actually, there's this guy called Joseph Fourier, a French mathematician, right? Showed that any periodic wave form can be generated by using a sum of sine waves and cosine waves. I mean, cosine again is a sine, but 90 degrees apart. So essentially, again, like we can do it using sines, but usually when we express it, we use cosines so that we can omit that 5/2 in that angle. So anyways, so this guy Fourier showed that while studying this heat flow, I'm also not sure how this related to heat flow, but he discovered that any complex signal can be given as a sum of sinusoids, right? So for example, now this slide has a sine wave A and a sine wave B and the addition of it, right? So how do you derive the addition? You take the amplitude, you go through the time. At any instance of time, you take this amplitude, you take this amplitude and add it together, right? So when both waveforms rise, you know, like they add, and then one waveform rises while the other goes down, they kind of attenuate each other, right? So I think you can intuitively see what you mean by combining two waveforms, right? So this guy Fourier showed that any arbitrary frequency, arbitrary waveform, a periodic, right? This wave has to be periodic. Any periodic waveform can be derived using multiple as a series. Sometimes the series is infinite, right? So complex waveforms, this series can be infinite, and it is just sometimes it's an approximation, right? But when the series goes to infinity, you can create any complex periodic waveform using sinusoids. Okay. Right. So again, like intuition, right? So let's get a visual intuition for this. Let me open up Desmos again. Can you guys see this screen? I assume that you can see, right? So here on my left side, I have a set of expressions, right? Set of waveforms. And let's see what they are, right? So first, I have sine 2π fx, right? So I have f as a variable, right? I have sine 2π fx, sine 2π 3fx, 2π 5fx, 7fx, and 9fx, right? So these are what we call harmonics of this fundamental frequency. So basically, this if I show this is twice the frequency, right? So in one cycle, sorry, three times. In one period of the fundamental frequency F1, this F3 completes 3 cycles, right? So we call this the third harmonic of this F1. So basically, that is also another term that you have to be familiar with. We talk a lot about harmonics in, and that we really don't want harmonics in our transceivers. So that's something that when we discuss about the quality of our transmitters, we need to be aware of this harmonics, right? So basically now, what I have here is a series of odd harmonics, right? So harmonic is an integer multiple of the fundamental frequency. In this case, the fundamental frequency is this f, and then this is 3f, 5f, 7f, and 9f, right? So if you see these frequencies, you can see. And then again, like I have this amplitude here is 1/3 of the third harmonic, 1/5 of the fifth harmonic, and then 1/7 of this harmonic, and 1/9 of this ninth harmonic, right? So, and then I have this other plot, right? So let me just to clarify, let me just keep the fundamental frequency. Let me just switch that as well, off that as. Let's keep this addition, this f. Let me keep on adding this odd harmonics, right? So let's add f3 to it. Okay. Now, this waveform is somewhat similar to a square wave, but still, there are certain dips here and there, And let's add the fifth harmonic as well. Let's add f5 to this. Okay. Things are getting better. Yeah. And then let me add the seventh harmonic. And let me add the ninth harmonic. Okay, now we are almost there, right? So it can be shown by using a Fourier transform that adding infinite number of odd harmonics to the fundamental gives you a square wave, right? Is this clear? Yes. Understood? Everybody, did you get this? Or do you need any clarity? තේරුණාද නැද්ද? හරි. Okay. අපි එහෙනම් කන්ටිනියු කරමු මේ විදියට ඕනම waveform එකක් ඕනම periodic waveform එකක් sinusoids වල එකතුවක් විදිහට පෙන්වන්න පුළුවන්. ඕගොල්ලන්ට මේක response වල try කරන්න. I'll share the links, right? Like try to do a triangle wave and like find out these periodic waves like a sawtooth, how to generate that, right? Okay, cool. How's it? Right, let me go back to my slide. And also there's this another interesting site that I found. I think I'll quickly show you an interactive introduction to Fourier transforms, right? So this is, I mean, this site also doesn't have like a lot of mathematics in it, but it's introduction, right? So, right. So remember that we showed that a sine wave can be given as a circular motion of a vector, and then this multiple circular harmonic motion combined can derive any arbitrary thing. So even this drawing, right? But I think more than this, what is important is if you go down, you have this certain demonstrations, right? This complex, somewhat complicated waveform is a sum of these two sine waves, right? And you can just play these sum and then play the right. So this is, I mean, again, like this is in real world you find this, right? For example, if you take music, like a sine wave just doesn't sound interesting, right? So if you play a note in a musical instrument, right, like a guitar or a piano, we say this note has a frequency, but that's just a fundamental frequency. But there's a lot of harmonics in that. That's what makes this musical note beautiful and interesting. So here you can okay, so this is a square wave demonstration that I showed you earlier, right? Here you can play around with that. You can change the number of harmonics, right? And then approximate the square wave. And it has even more interesting one here. You can draw an arbitrary waveform, right? Something like this. And then it will do the Fourier transform for you and derive all the fundamental components of it, right? So you can kind of like, okay, add and remove these different components of it, right? So, yeah. Okay, then there's a lot more interesting stuff that you can do here. So please do that, go in your own time, right? Let me go back to the slideshow. Okay, so now I think this is just a recap about harmonics here, right? Harmonic is a frequency that's a whole number multiple of the fundamental, right? So like when you learn about harmonics, like if the fundamental frequency is, let's say, for example, let's take a tight string, right? I mean, maybe a guitar string on a guitar, right? When you pluck it, it oscillates at the fundamental frequency, right? But it can also oscillate twice that, right? So basically, so that's what a harmonic is, an integer multiple of the fundamental frequency. And when it comes to these radio transmissions, let's say, for example, we have a transceiver that transmits at 144,440 decimal, right? But we don't want any harmonics. Usually oscillators and our RF amplifiers and things like that tend to generate harmonics, right? So the quality of a transceiver depends on the spurious transmissions. We call the unwanted transmissions. It has to be low. For example, if you take this cheap Chinese handhelds, and if you transmit and view the spectrum of it, then you will see that there are a lot of harmonics in it, right? Okay, so that's about harmonics. Yeah. I hope everybody got a clear understanding of that. And okay, so as a natural progression of the discussion about, like we said that any complex waveform can be represented by a set of sine waves, right? Now, this gives us another way of representing a waveform, right? So far, we've dealt with time domain. Like time domain. So the domain of a function is the set of values that we take as the input of that function, right? So in the case of that, like the y t equals sine 2 phi ft, the input is the domain. Input is a time, right? So now, in terms of the frequency domain, if we show a signal in frequency domain, the x-axis is frequency, right? And then the y-axis remains the same in the amplitude. This can be done because we can represent any complicated waveform as a sum of a series of sinusoids, right? So in the frequency domain, what it shows is which frequencies are present and how strong each frequency is, right? So amplitude of each frequency. So I think again, like this calls for a visual intuition, right? So again, let's go back to our faithful friend here, Desmos, right? Oh, sorry. Oh, okay. I think I forgot to make it as a link. Let me just quickly stop this and copy it. Just okay. Okay, let me just quickly get it here. I hope it is clear to you guys, right? So basically, again, this is my earlier kind of like example, but now I've graphed this in the 3D graphing calculator mode. So again, like this is familiar, right? So this is equals 4/5 times sine omega t, 1/3 of 3 omega t, and 1/5 of 5 omega t. Again, like here I use the omega notation. Omega is nothing but 2 phi f, right? So I use, to make it simpler, I use this angular velocity here, right? So it's nothing but 2 phi f here. So this is the identical expression here, right? So now I have this wave, which is a sum of these three sinusoids, right? And then I have them plotted here, right? So now here, this is my time domain view, right, of this. But if I kind of like do this like this, now, because I push these waveforms in the y-axis here, right? So this is my fundamental, forget this negative part, right? No, this is just for visual intuition, right? So you can't just do a Fourier transformation like this, but remember, I have this fundamental with this amplitude, right? Forget the negative part here. And then the third harmonic, 1/3 of the amplitude. The fifth harmonic, 1/5 of the amplitude, right? So this part, if you take this quadrant, right, this is what a frequency domain representation is, right? So this is a visual intuition, right? So you need to learn a bit of maths if you want to really do a Fourier transform. But this is what a spectrum view is, essentially, right? Exclude the other quadrants here on this Cartesian plane. This positive quadrant, y and x, the positive quadrant, this first quadrant here, this is essentially what a frequency domain representation of this signal looks like. Okay, so this complex signal is made up of these three parts with these amplitudes, right? So this is what a frequency domain representation is. Now it is crucial to get the intuition about this. I mean, it's not necessary to understand the deep mathematics that goes into this, but it's crucial that we get a visual understanding of what a frequency domain representation is. Is this clear to everybody? Yeah. Any questions? If there are any questions, please feel free to ask. Okay. Yeah. Okay, then let me go back to the slide deck. And also another thing that I would like to give you this kind of like an idea, since we are here. I think about this. Now this is a rotating vector that projects this sine wave, right? What if this vector rotates the other way? What will be the result? You know, it's again like a bit, it's a bit of an advanced topic, but that's what we call a negative frequency. It's the same waveform, but the frequency is negative. So something to think about, you know. So when we deal with GNU radio and then this complex waveforms, this idea of this negative frequency comes. So it's nothing but the same vector rotating the other way around. If you only take the projection on one axis, we can't distinguish between positive and negative frequencies. But if you represent it in quadrature form, you can distinguish between positive and negative. But that's just something that came into my mind. I just want to tell you guys while we are looking at this. Anyway, let me go back to where we stopped from. Right. Oh. Okay. Okay, now, yeah, I think this is where we stopped. Right. Now, there's this other concept. All right. This concept of a bandwidth. Now, earlier we talked about sine waves, right? There's one frequency. Right now, complex waveforms, we said that they take they are comprised of multiple sine waves. So essentially, a bandwidth of a signal is the range of frequencies that it occupies. From the highest frequency component to the lowest, what is the range? Right? Okay. So I'll ask a question, since nobody is like looks like everybody understood this everything perfectly. Let me ask you a question. If I have a 1 kilohertz sine wave, what is the bandwidth of that? Anybody? What is the bandwidth of a 1 kilohertz sine wave? කාට හරි කියන්න පුළුවන්ද? මේ definition එක පාවිච්චි කරලා apply කරලා පුළුවන්ද කියන්න? දැන් මෙහෙම හැමෝම දැන් හැම් රේඩියෝ ඔපරේටර්ස් වල ඉන්න මයික් එකට මයික් ෂයි වෙලා බෑ. හැමදාම FT8 තමයි කර ඉන්න වෙන්නේ. එහෙම නැත්නම් එහෙම මයික් එකට කතා කරන්න ලැජ්ජ වෙන්න එපා. So being a ham radio is knowing this technology and electronics and the procedures is one thing. Not being shy to speak up and talking with people all over the world is a big part of it, right? Otherwise you will end up doing just FT810 doing experiments and all that. Well, there are some people who does that. We have some hams you never speak on the band, but I hope you guys are ready to speak. Anybody can tell me the bandwidth of a 1 kilohertz sine wave? Or for that matter, what's the bandwidth of a 1 megahertz sine wave? Okay. Bindu, right? 0. It's just one frequency, right? So by definition, it's f max minus f min. So it's the same for a sine wave, and the bandwidth is 0. Okay. So now this bandwidth is important because if we are occupying more frequencies on the spectrum, we'll talk about spectrum on the next slide, then we are basically occupying real estate. It's like occupying land or something like that, because the RF spectrum is shared. So when we communicate, we tend to keep this bandwidth to the bare minimum, right? So we'll discuss about that when we talk about modulation as well, right? So so I mean, we don't have to worry about this. Different modulation types occupy different bandwidths, like continuous wave CW, Morse code takes the lowest, and then SSB, single sideband, AM, and then FM takes more bandwidth, and digital data modes. I'm not too sure whether this is 100% correct. Some digital data modes don't take much bandwidth as voice, right? So this needs to be corrected, but yeah, that's a mistake on my end. That's what you get for using Claude to generate the slides. Yeah. The bane of using the AI age. Anyway, narrow bandwidth improves signal to noise ratio. So basically now this RF spectrum also carry noise, like noise gets induced, there are different waveforms, and then there's like power line noise and all that. So if your bandwidth is narrow, you are less susceptible for noise, because if you use a narrow band of the spectrum, then the amount of noise you capture is also narrower, right? And this channel spacing and band plans allocate bandwidth to prevent adjacent channel overlap. So basically, we'll talk a bit about that when we talk about modulation, right? So because now complex radio frequency waveform doesn't just occupy one frequency. Although we say, like, let's say for example, even though we say that Sirius FM is at, I don't know, 101 megahertz, it's centered at 101 megahertz, but there's a bit of spectrum that it carries. So what that means is, if Sirius is in 100, you can't just give 100.1 to another channel, right? So depending on the type of modulation, we will talk about that later when we go forward. Okay, so that the concept of bandwidth, I think, is that clear to everybody? Yeah. Okay, I assume it's clear since there are nobody is talking. Yeah, I'll continue. Okay, so yeah, cool. And then let's talk a bit about RF spectrum here, right? So we know what frequency is, and then depending on the frequency, we roughly divide this into 12 decade-wide bands, right? So each band is a decade, like 3 to 30, 30 to 300, like that, right? So 10 times the start. So 3 times 10, like that. So in decades, right? So each band we multiply by 10. That's what we call decade-wide bands, right? So it's a multiple of 10. So there are now this is why do we have these bands? It's for ease of communication, and also like to divide this up and allocate, like rather than giving a precise frequency range when we communicate, we say HF or VHF. In terms of like transceivers also, we say, okay, I have HF transceiver and then VHF transceiver, right? So there are this ITU. I think you come across, most probably come across ITU in earlier classes. The International Telecommunication Union is the governing body that manages the spectrum worldwide, right? So basically, ITU is the controlling body that allocates these frequencies to different services, like, like military, broadcast, weather, telemetry, and GSM communication, 4G, everything like this. ITU is the governing body, and all countries respect these allocations. Expect sometimes like countries like where like US, where Trump is, and the FCC kind of like tries to allocate our ham frequencies to commercial providers, but thankfully, worldwide ITU is kind of have a bit of a hold on this. So, but it's a fight, right? So sometimes if FCC tends to allocate, I mean, even these days, I think they've allocated a frequency from our UHF ham allocation to some commercial satellites. Yeah, so you can read about that in the news. Anyways, so out of the 12 bands, I've listed out 8 here, right? Because those are the bands that are used for very commonly for radio communication, right? So from VLF, very low frequencies like 3 to 10 kilohertz. If you can see the frequency, these are like in terms of audio these are starting from the audio range, right? 3 kilohertz is an audible tone as well, right? So these things are used mainly when we communicate with submarines, right? So that because these high frequency radio waves don't penetrate water, go through water easily. Because of that, when we communicate with submarines, we use these VLF signals, and also like if when you use lower frequencies, we have to be wary of the bandwidth. With low frequencies, you can't transmit a lot of bandwidth. That is got to do with, I mean, if you have studied the Nyquist-Shannon sampling theorem, like the amount of data that can be encoded is directly proportional to the sampling rate. So with low frequencies, the bandwidth that you can use gets reduced as well. So that's why we are bandwidth conscious when you are using lower frequencies like HF. That's why we use single sideband on the low bandwidth modes like SSB on HF. But when we go to VHF, we don't really care about that, and we use this narrow band FM or wide band FM. Right. And when you go to this satellite range and these high frequencies, you can get higher bandwidth. So that's why this 5G uses very high frequencies, and you get very high data rates on these 5G frequencies. You can't do the same on low frequencies. That's something for you to study on your own, right? Yeah. So also this is the RF frequency spectrum. Okay. Yeah, the time is 10:38 now. Aruna, shall we continue a bit more? Fine, right?
How many more minutes you will need, Chamit?
So, I mean, yeah, so I can stop here, or I can talk a bit about modulation.
Modulation, then we'll stop.
Yeah.
We can take 10-15 minutes to speak about
modulation and all
introduction.
That,
yeah. Then we can continue next week the rest.
Sure, we can do that. Maybe to keep things interesting, I'll show you one demo from GNU Radio. We just briefly talk. Give me about 15 more minutes. We'll do that, and then we'll pause for today, and then we'll continue hopefully from next week. If I can prepare the content for another day. Yeah. But anyways, let's continue. Okay, so what is the communication system? Now we are talking about radio theory and communication, right? So essentially, what is the communication system, right? We need to take data from one point to another point, right? So basically, in the case of radio communication or electronic communication, right? Essentially, we have an information source, right? It can be my speech, it can be a image, right, in front of a video camera or a still camera even. It can be the stuff I type on a keyboard, right? And then basically we need to convert that to electrical signal, right? So for that, what we use a transducer, an input transducer, right? In the case of a walkie-talkie or a transceiver, we use a microphone, right? And in the case of a image, we can use the CMOS or the CCD sensor inside the camera, right, to capture that. And then somehow we need to transmit that across, right? And then for that we use a channel. The channel can be the vacuum or the open air in the case of radio frequencies. And in case of, let's say, our network communication, your internet, it can be your fiber link, right? And it might take multiple channels to go to the destination. In the case of like this fiber, it might take the fiber link and then a satellite link and then again to the destination and the fiber link, right? Or electrical link as well, right? Last mile is typically electrical. So we have a channel, and then the channels can introduce unwanted signals as well, what we call noise, right? So power line hum, lightning, radio frequencies generated by lightning in the case of like FM, AM transmissions, right? The channel can carry noise, right? And then we have a receiver, right? An electronic circuit or optical circuit, in the case of fiber, that receives it and converts it to an electrical signal, and then an output transducer converts it to conveys it to the destination. In the case of this old video, my camera feed, you see it on the screen, and you hear my audio on the speaker of your laptop, right? So this is a typical communication system. The channels might vary, the transmitters might have, like different architectures, and we might use different transducers. But what a communication system essentially does is takes information from an information source and takes it to the destination. Yeah. So what is modulation? Why do we need modulation to transmit this information or intelligence from one point to the other, right? What modulation means is basically our intended signal that we need to carry. In terms of this modulation lingo, we call it baseband. Our baseband signal, we somehow embed it in a higher frequency signal, right? Why? There are several reasons. One thing is we can keep antennas a practical size, right? I think we did this calculation earlier for a 10 kilohertz signal. The wavelength was 30 meters, if I'm not mistaken, right? And assume that we need to transmit some audio, like say 3 kilohertz signal as a RF signal. The length of the antenna will be thousands of meters, right? So basically, again, like I think we have to come to this in the future. But when we design antennas, antenna length relates to the wavelength, right? So it can be like a quarter wave with a vertical antenna that's one quarter of the wavelength, or like a dipole can be half of a wavelength. So like that. So the antennas relate to the frequency that we want to, antenna dimensions relate to the frequency that we want to transmit or receive, right? So to keep the antennas parallel side. And then long distance propagation, right? So for example, lower frequencies, the energy field is weaker, right? Energy, so that we can't, I mean, the propagation is weak. And then higher frequencies we can send further, right? And lets many signals share the spectrum. So for example, now if we just transmit the baseband, let's say hypothetically, even though it's impractical, we can transmit audio frequencies. Then if we transmit two audio frequencies from two stations, they share the same spectrum and they interfere. So by modulating, you can move this, our baseband, to a free slot on the RF spectrum. Yeah. And then receivers demodulate the carrier to recover the message. So the carrier frequency, the modulated carrier, we receive it and then we demodulate to do that. There are various forms of modulation. I mean, we discussed about waveforms, and there are certain properties of waveforms, right? So we can embed this baseband in any of those properties. For example, amplitude modulation, you can change the amplitude of the wave, as a function of the baseband. We can change the frequency, and we can change the phase, right? As well, and there are digital forms as well. Like amplitude shift key, it's type of amplitude modulation, but for digital signals. But we are not going to talk about those in length. I just noted it down here. You guys can refer to it, right? So that is modulation. So this is a block diagram of a modulator and a demodulator, how this thing works. Like basically you have the baseband signal and a oscillator that oscillates at the radio RF frequency, and then the modulator. Typically, this is a mixer. Typically modulation means mathematically multiplying the signals together, right? And then it generates the modulated RF, and the modulated RF is not just one frequency, it's a spectrum of frequencies, right? So then with demodulator, on the other side, receiver side, we demodulate, and we use a local oscillator. Typically, sometimes, like for some modulation types, we don't even need a local oscillator, but we typically use a local oscillator to be efficient. But we'll discuss about those things later. And then we get the recovered message. Right. So we'll talk a bit about amplitude modulation. I think, let me just discuss these 3 slides and then 4 slides. I'll show you a demo, and then we'll stop for today, right? Maybe 10 more minutes. So amplitude modulation is, what we do is the carrier's amplitude we modulate with the message signal. What that means is when the baseband signal amplitude increases, we increase the carrier's amplitude, like that. So it produces a carrier plus 2 sidebands. So now, if we look at the spectrum of a modulated signal, the frequency components, the carrier is there, and there are 2 sidebands, what we call the upper sideband and the lower sideband, that is just above the carrier and below the carrier, that actually carries the information. The carrier, the frequency component of the carrier doesn't have any, doesn't carry any intelligence or any data. The data is carried on both sidebands equally, right? So now, what are the strengths and limitations of amplitude modulation? The biggest advantage of AM is that the receiver is fairly simple, right? So I don't know whether you guys, I know, like when I grew up, when I was a kid, AM radio was here, AM and like what you call medium wave and short wave, amplitude modulated broadcast radio stations were there, and we used to build these very simple radios, like what you do this කම්බි වැටට වයර් එකක් ගැට ගහලා ඩයෝඩ් එකක් දාලා කැප් එකක් දාලා පොඩි ක්‍රිස්ටල් ඉයර්ෆෝන් එකකින් රේඩියෝ අහන්න පුළුවන් ඒ දවස්වල. Now unfortunately now you can't do that. So the receivers are very simple, right? Because of that, amplitude modulation is used in broadcast. And broadcast stations වල අපි amplitude modulation use කරනවා. මොකද receiver side එක simple. මොකද broadcast ගත්තාම we have like a lot of receivers, one broadcast station. So having a complicated setup in the broadcasting is okay, because like it's power inefficient, but AM is very power inefficient. Like a AM broadcast station is you need like kilowatts to transmit. But if you take an FM transmission station, like you talk in the range of like hundreds of watts to a kilowatt, right? A medium wave stations are like tens and sometimes even hundreds of kilowatts. I think in US you get like stations that operate at close to a megawatt even, right? So, and it is susceptible to amplitude, noise, and static, right? So basically, because we are changing the amplitude, it is susceptible to noise. So for example, when you add your signal with the noise, then like if there's any noise wave at any frequency, this our amplitude also changes. So I mean, I think when we do demonstrations, I have a bit of a demo about that as well, but maybe for a later date. Okay. So AM broadcast, AM is used in broadcast, and also airband voice communication uses this, like from aircraft to aircraft and aircraft to ground communication. In aviation, we use AM. That is due to a key property of AM. Even if two people transmit at the same time, we can, in FM, the stronger frequency takes precedence and it drowns out the other station. But in AM, you can even hear both stations. You know, like the weaker one will be weaker, but you can hear both. So because of that, AM is a safer alternative for airband communication because of that, and other historical reasons as well. Okay, now, so this is like a simple diagram showing the baseband here. My message signal is my baseband, and this is my AM signal, and this is the multiplication of the two signals. This is what a AM modulated signal looks like. Okay, so if you can see closely, if you see the envelope of the outer part of the carrier, it has the baseband signal in it. So you can use what we call an envelope detector or a simple circuit to demodulate AM, right? Anyways, now let's let's stop from here. Okay, so no, let me just use these two slides, and then we'll do a short demo, and then we'll wrap up. So this is the if you modulate a sine wave, sinusoid with a carrier, this is what the spectrum looks like, right? So you have the carrier FC, and you have FC plus FM, that's a baseband signal, FC minus FM. So this is the spectrum, and the bandwidth that is taken is 2 times the bandwidth of the modulated, the baseband, right? In the case of a sine wave, I think you can do this. You can prove this in mathematically as well. Actually, this is multiplying 2 cosine waves together. You know, like if you remember your A-level maths, you know, like when cos A cos into cos B is cos A plus B cos A minus B. So this is the 2 components, A plus B and A minus B. Just you know, something that if you know about bit about maths, you can get an idea about this. Anyways, now what if I modulate something like a voice signal in this? So this is what it looks like, because a voice signal is not just one frequency. You know, there are the shape of this sideband is might not be exactly this, but you know, it occupies the entire range as the frequency varies, right? So this is what the spectrum view looks like for amplitude modulated signal. Okay, then without further ado, let me fire up this. Let me close this slideshow, and let me go to this, right? So this software that I am using, let me give you guys a brief intro to this, right? This is what we called GNU radio or GNU radio. Actually, it's a library written in C++ to do this radio model and do radio work using software, right? So this is used for what we call software-defined radio. For example, now when we talked about modulation and all these things, we discussed that most of these operations are mathematical operations, right? So a computer can do mathematical operations very fast, right? So if we can somehow convert our signals into digital representations, and then we can do these modulation, demodulation, and anything in software, right? So basically, GNU radio does that. Now, the software I am using is what we call the GNU radio companion that lets me write GNU radio code using a GUI, kind of like a flow graph interface. This is what we call a flow graph. So we connect these sources blocks together. So signals flow from one block to the other, connected blocks, right? So actually what this does is this generates a Python file, Python code that actually runs, right? So let me just briefly show you what this is. Let me just first, can I zoom? Yeah. So if I choose this, I mean, if I explain this, first I have a signal source here, right? So this is my signal source with a frequency of 5,000, right? 5,000 hertz, right? And then I feed it to this throttle block. So this throttle block is a bit of a, I mean, this is not a functional block that we require, but if we, I mean, when we flow packets from one block to the other, if we have hardware piece in it, the hardware decides the rate of the how the packets are given out. But in this case, this is a software-based source. We need to throttle it, right? So this is something that, I mean, I'm not going to discuss a lot about these concepts. I'm also not an expert of this. So I'm also learning how to use GNU radio, but I thought of showing this to you guys because this is pretty interesting. And because this can also work with hardware as well. You know, if you have SDR dongle, you can plug it in, and there's an ADSB source here for this ADSB TV chip-based dongles. You can get the quadrature signal, the IQ signal from that, and do your signal processing, demodulation and stuff like in this software, right? And if you have something like a HackRF1 that is capable of transmitting, you can generate, I mean, you can do various like stuff, a lot of stuff with this GNU radio. Anyway, so back to this flow graph, right? So basically, now then I have throttled it, and then directly I have this QT-GUI time sync. So basically, a QT-GUI time sync is basically, it's like an oscilloscope that shows a time domain signal or multiple signals in this case. So here I'm showing 3 signals, right? And then, so basically my my sine source, this is my baseband at 5 kilohertz, right? And then I have another signal. Sorry, this is my carrier. 5 kilohertz is my carrier. And then this is my baseband signal, which is 300 hertz and 500 millivolt amplitude, right? And then I have offset here. We need to give it a DC offset because otherwise it's not amplitude modulation. It will be double sideband suppressed carrier if you don't have a DC offset. So this is again like goes into a bit of the nitty-gritty maths of amplitude modulation. I'm not going to discuss that. It's for you to find out. There's a YouTube video channel called All About Electronics. It has a very good playlist about this it goes very deep into the mathematical aspect of these modulations. Anyway, so we have the signal source, and then what I'm doing is multiply. So I told you, like, so essentially this mixing of two signals is like essentially multiplying it, and then I send it to time sync as well as a frequency sync. This frequency sync is basically spectrum analyzer. You know, like a software-based spectrum analyzer. It uses the fast Fourier transformation to display a frequency domain representation. Okay, so I think that covered it. Let me just run it for you guys. Right. So now what this does is this generates a Python code and runs it. Right. So okay, so this is, let me just first switch off these signals. Now in green, I see my carrier, right? So this is my constant amplitude carrier signal, right? And then, sorry, this is my baseband signal, right? Remember that we need to, I told you that we need to add a DC offset, so that's why it's not at 0. And this is my baseband, and this is my, sorry. Oh. This is my modulator signal, right? So this is my envelope, right? And then this is my FFT plot. This is my spectrum, right? So in the center, I don't know whether you can see this. I have, this is the carrier, right? 5 kilohertz carrier. And then this is 5 plus that 300, 5.3 megahertz. And this is the upper side band. So this is the lower side band, 5 minus, what you call this, 300 hertz, right? Okay, so yeah, and then by changing the amplitude of the base band, I can control what we call the depth of modulation or the modulation index, right? So when I increase the modulation index, so I think I have a label here showing the modulation index, right? I don't know if you guys can see this, but when I increase the modulation index to 100% or 1, what happens is that the carrier wave goes all the way down to 0. You know, like when my baseband signal swings to the minimum, the carrier also goes to signal. So this is what we call 100% modulation, right? And then we have, if we go over 100%, actually we distort the signal. Now, if you go over, sorry. Okay, for some weird reason I can't do it. Okay, like that. You know, like you get a distortion and then the carriers face inwards. So yeah. Alrighty. Yeah, any questions? I mean, I highly encourage you guys to download GNU Radio and then play around with it. I'll also share these my flow graphs with you guys so you can just run it. I have some other stuff as well for a demonstration of AM and FM. I can share those with you guys. So yeah, I'll open the floor for any questions. Any questions, guys? So any questions about GNU Radio and anything that we any questions about what we discussed so far?
I think this part is very important. What Chamidu said, make a over modulation, under modulation, exam questions. So we have to know all these things, you know, under modulation, over modulation, in 100% modulation. අපි සාමාන්‍ය ගන්න ඇති එක හේතුවක් තමයි under over modulate වුණාම distort වෙන හින්දා ඒවා දැනගන්න ඕනේ ඒ ටික අහනවා පොඩ්ඩක්. හැබැයි මේ demonstration එක maybe what he has presented is little advanced with some technical terms, but හැබැයි මේ ටික these things are needed for your exams. You know, general class, advanced class exam, they are specifically asking about the under modulation, over modulation. Anit එක තව announcement එකක් I want to make, because there are people who have applied for membership, they have not submitted all their documents. හුඟක් අය සමහර documents submit කරලා නැහැ. ඉතින් ඒකින්ද best if you can see that you may have got an email messages asking those documents. Please submit your documents, then you will get the membership immediately, right? ඉතින් ඒ ටිකත් submit කළා මේව කරන්න. So coming to good session, පොඩ්ඩක් advance වගේ තිබුණත් those are things we have to look at, but demonstrations are very good, really. Very good demonstrations, Shamidu.
Yeah, thank you. Yeah, Aruna. So basically, I think even though you might not use this, you might not download radio and all that and understand how this works 100%. I also don't understand, a lot of it because this you need to learn about this lot of like DSP when you work on GNU radio to 100% understand that you need complex numbers and all these transforms like Fourier transform and Hilbert transform and all that. You need to be aware of that. Yeah, but I mean, to have a visual intuition is what matters as ham radio operators. To get a visual intuition and understand, to build something like this, play around with it. The next time I'll also show you guys actual demonstration of some audio transmitted over a network channel, not antenna, and then modulated and transmitted over a network channel, and then we get it and then we demodulate FM and as well as AM and show it to you guys, and we can like see the characteristics of how these things behave, like in terms of channel noise. Like I have this demo where you can inject some channel noise into a FM AM modulator versus an FM modulator and how these things react. Like I like when we learn about these things, we say like AM is more susceptible to noise and FM is immune. It's not 100% immune though. So like having building this and testing it out for yourselves gives you like a kind of like a mental picture. That's the most important thing I think, even though if you don't understand this nitty-gritty mathematics. Yeah. Okay, then thank you guys. Thank you very much. I'll share the link with this to download this GNU radio, as well as like this Desmos, my links, the demo links for Desmos. And yeah, let's hopefully let's see you guys next week. I mean, if I'm a bit these days, if I cannot prepare the content for the next week, I will see you the week after.
Yeah, we'll see, Shamidu, if you can't continue. So Taranga will continue the balance part of his licensing condition and procedures and everything. So then we can have another session for these these modulation and frequencies, bandwidth and all that, because that part is very important, because that is the ham radio, we see. All right.
Thank you guys.
අද නවත්තමු. අදට නවත්තලා මෙසුමාඩල කන්ටිනියු කරමු. ප්‍රශ්න තියෙනවා නම්
මොකද හිතන්නේ මේ ඇත්තට මට පිට ෆීඩ්බැක් එකක් දෙන්න පුළුවන් නම් හොඳයි. ඔයගොල්ලෝ ඒ කියන්නේ ඔයගොල්ලන්ට මේක තේරුණාද, මේක වැඩක් තියනවද නැත්ද? මොකද මේක බේසිකලි දැන් මගේ අන්ඩර්ස්ටෑන්ඩින් එකෙන් මට හිතෙන දේවල් තමයි මම මේ ප්‍රසන්ට් කරන්නේ. එතකොට ඔයගොල්ලන්ට මීට වඩා දෙයක් ඕනද නැත්නම් වෙන දේවල් ඕනද? ඒ ඔක්කොම ඔයගොල්ලෝ කියන්න ඕනේ ඇත්තටම. ඉන්ටරැක්ටිව් මොකද ඉන්ටරැක්ටිව් මේ විදිහට මේක කරන්න පුළුවන් නම් මම ගොඩක් කැමතියි. මොකද එතකොට දැන් මමත් නොදන්න දේවල් ගොඩක් තියෙනවා. we can research together and we can learn together, because I'm also learning. I am pretty much interested in this DSP and this GNU radio. So I just started learning this as well. So if you guys overlook make a put up balala, then we can discuss, because some of these things are like sometimes not straightforward as well. Some other holographic adha වැඩ කරන්නේ නැහැ. බලනකොට sample rate එක මදි Nyquist මේක නිසා alias වෙනවා. ඔය වගේ ප්‍රශ්න ගොඩක් එනවා. ඉතින් මේක කරලා බලද්දි අර it's a very interesting thing to learn, because the best thing is you don't even need license, because you are not actually transmitting. You can just transmit to via a 0MQ channel and then over the network to different PCO to the same PC, and you can run to GNU radio apps and then do this analysis and development. Anyways, yeah, hari එහෙනම් තරංගත් ආවනේ අපෝ.
ආවා පොඩ්ඩක් ඩ්‍රොප් වුණා. ශාවෙන්දු මේ මම සජෙස්ට් කරන්න ඉතින් අපි මේ GNU රේඩියෝ වලට වෙනම ටිකක් එක්ස්ටෙන්ඩඩ් සෙෂන් එකක් වෙනම කරමු. මේ
ඒක තමයි.
සෙෂන්ස් කීපයක්.
ඒක
නම් ප්‍රැක්ටිකල් ඇක්ටිවිටීස් එහෙම නේද?
ඒක නම් හුඟක් හොඳයි තරංග ඇත්තට. මොකද අපි ඇඩ්වාන්ස් වෙන්න ඕනේ ඉස්සරහට. ඒක ටීම් රේඩියෝ ගැන මෙෂ් නෙට්වර්ක් ගැන ඒවා නැත්තම් හරියට අපි කට්ටිය සමහර අය නිකන් පොඩ්ඩක් මිස්ලීඩ් වෙනවා ඒවට. මිස්ලීඩ් කරගන්නවා ඒ ටෙක්නොලොජිස් එක. so we'll see. ඒකයි තරංග පොඩ්ඩක් බලමුකෝ අපිට ප්‍රැක්ටිකල් සෙෂන් එකකුත් මේ අතරට දාගන්න. එතකොට පොඩ්ඩක් කට්ටියගේ කොයි වගේ Q teacher එකක්ද කියන එක මට තාම අයිඩියා එකක් නැහැ.
ඒක මෙහෙමයි යන්න තමයි. ප්‍රැක්ටිකල් සෙෂන් එකක් අපිට කරන්න පුළුවන් නේද ඔය පොඩි නිකන් ඔය දැන් මේ වගේ මොඩියුලේෂන් වගේ වුණත් අපිට ප්‍රැක්ටිකලි කරලා බලන්න පුළුවන්. අපේ ගාව තියෙනවා සිග්නල් ජෙනරේටර්ස්, ඔසිලොස්කෝප්ස් ඔවා ගෙනල්ලා පොඩ්ඩක් කට්ටියත් එක්ක එකට වාඩි වෙලා
ඒක
පොඩි
තමයි
සෙෂන්ස් ටිකක් කරන්න පුළුවන් නේද? ඒ කියන්නේ ප්‍රැක්ටිකලි. ඒ කියන්නේ බේසිකලි ඔය දැන් එන මේ මොනවද මේ ඔය සිග්නල්
දැකලා තියෙන්නේ නම් ඔක්කොම රිසෝසස් තියෙනවා තරංග ගාව. ඉතින් කුරු නෑ ගලා. චමිතු ගාවක් තියෙනවද? මම දැවතාව දැකලා
ටිකක් තියෙනවා ඇත්තටම.
එහෙනම් අපි චමිතු පොඩ්ඩක් එක ඔසිලොස්කෝප් ස්පෙක්ට්‍රම් ඇනලයිසර්ස් එහෙම තියෙනවනම් පොඩ්ඩක් බලලා පොඩ්ඩක් අපි එහෙනම් අපි චමිතු එක සෙෂන් එකක් දාමු. පුළුවන් වෙයිද ඔයාලට ෆැසිලිටේට් කරන්න?
අපි ප්‍රැක්ටිකලි කරමු. අපි ඊළඟට තියරි සෙෂන් එකක් අපි මෙහෙම කතා කරලා අපි ප්‍රැක්ටිකල් සෙෂන් එකක් දාමු. ඒ කියන්නේ basically to let them play around with these tools ටික ගෙනල්ලා අපි දවසක සෙට් කරලා නේද?
ඔව් මේ පාර තුනක් දාන්න මගේ අයිඩියා එකක් තියෙනවා. එහෙනම් චමිදු එකක් දාමු. ඊට පස්සේ අපි කුරුණෑගලත් එකක් දාමු. ඊට පස්සේ හදිස්සියේ ජාලියාවොත් තවත් එකක් දාමු. ඔය ඇන්ටෙනාස් ගැන ඒව ගැන ෆීල්ඩ් වර්ක්ෂොප් එකකුත් දාගමු අපි.
හරි.
මේ මම කියන්නේ ඉතින් ඇන්ටනා වර්ක්ෂොප් එක ඒක අනිවාර්යෙන් දාන්න මේ අපි
ඔව් ඒක නම් දාන්න මම ආපු ගමන්
කරන්න මේ මොකද කීප දෙනෙක්ගෙම එල්ලීම් තියෙනවා ඇන්ටනාස් හදන්න දැන් කට්ටියක් තනියම හැදුවා එකක් මාල්ලේම මේ ඒක පොඩ්ඩක් අපි චමිදුත් ඉන්න හින්දා මේ පොඩ්ඩක් ඒක ඔළුවේ තියාගමු ඇන්ටනා සෙෂන් එක. අනිත් එක චමිදු මේ අද හරි හෙට හරි පුළුවන් නම් පොඩි ඇක්ටිවිටි එකක් දාන්න ඩෙස්මොස් and GNU රේඩියෝ කට්ටියට කරන්න. එතකොට ටිකක් කෝල් එකක් තියෙනවනේ.
ඒක
right okay ඔව් මම මේක හෙට විතර වගේ දාන්නද?
ඔව් හදිස්සියක් නැහැ ඔයා හිමින් දාන්න. සතියක් තියනනේ කරන්න.
හරි එහෙනම් good night. හොඳයි thank you. Thank you for the participation.
Nice session, great session.
Very good session.
Good night.
Good night.
Thank you and good night.
ප්‍රශ්න එහෙම තියෙනවා නම් දාන්න මේ සෙෂන් එකේ පස්සේ
WhatsApp එකෙන් දාන්න.
WhatsApp එකේ. හරි අපි කෝල් කරලා ඒකට ආන්සර් කරන්න.
okay
okay good night.
good night bye
Night.
Thank you.